Welcome to the next video in measure theory and probability. This is video 11 on the monotone class theorem. It corresponds to part 1, chapter 1, section 4 of the textbook. Now, first, a definition. This is very similar to a sigma field, but it is, in a sense, more restricted in that, like, there are fewer assumptions. So in a sense, you have, like, less to work with, I guess you could say. So let E be any set and take some subset of the power set. So far, that's just like a sigma field. Now, this collection is called a monotone class if the following three properties are satisfied. Just like with a sigma field, we require the entire universe to be in the class. Now, instead of closure under complements, we talk about this if you have some two elements of your class, and if A is a subset of B, then the relative complement is in the class, right? So a kind of weakening, I suppose you could call it, of the complement law. And then also a weakening of the union law. So this time, if you have a countable collection in your class, and if they form an increasing chain, then their union is in the class. Now, just as with sigma fields, we can talk about the, taking some subset of the power set which may not be a monotone class, but then we find the monotone class that it generates, and just as before, just as with sigma fields, this is defined as the intersection over all monotone classes that contain C. So again, we are assuming that we take some collection out of the power set which is closed under finite intersection. It is very simple. I've already kind of talked about this, but showing that the monotone class generated by C is a subset of the sigma field generated by C, we're trying to show that they're equal, right? To show this direction of the subset is really trivial, and so I'm not going to get into it. It's basically the same as what we were talking about as like background to this theorem. So I'm not going to show that direction unless somebody requests it. So we only have to show the reverse. And it turns out that in showing the reverse, we can just show that the monotone class is a sigma field, because if it is a sigma field, then it must contain the smallest sigma field that contains the class C. So we just need to show that this monotone class generated by C is a sigma field under this assumption. And to show that it is a sigma field, I mean, we could try to do it directly, but really the easiest way to go about this is to use that thing that I said at the very beginning, which is that if we could show that this thing, which we already know to be a monotone class, is further closed under finite intersection, which is a pretty reasonable way to try to approach this proof. If we know that C is itself closed under finite intersection, then, it kind of makes sense to approach proving that the monotone class that it generates is closed under finite intersection. Should be a relatively achievable goal, and once we have it, it follows immediately from the things we've already talked about that it is a sigma field. So that's what we're going to try to do, right? We're just going to try to show that this monotone class generated by C is closed under finite intersection. Now that, having said that, maybe I've made it sound like this is going to be easy. Well, even with this strategy, it's still not going to be especially easy. If you try to do it yourself, you'll probably find that proving closure under finite intersection is quite hard. And so we are going to approach this in smaller, more manageable stages. So rather than trying to show that any two things in the monotone class have their intersection in the monotone class, instead, we'll take a more restricted assumption, right? We're not going to just assume that this set A is in the monotone class, we'll actually assume that it's in the generator, which is maybe a little easier because we're assuming that the generator is closed under finite intersection, so maybe we have a little more traction on that. So we're going to take something out of the generator and something out of the monotone class and try to show that their intersection is in the monotone class. Once we have that, we can kind of leverage that result to help us with other results that'll eventually get us to the sort of conclusion of the proof. Okay, so there's our intermediate goal, right? Take A in the generator, take B in the monotone class, and try to show that A intersect B is in the monotone class. Okay, so we will, in fact, first form this new collection we're calling M sub A, and it will be the collection of all elements in the monotone class with their intersection, right, such that the intersection with A is in the monotone class. And the idea here is that we would like to show that MA is some monotone class that contains the collection C, because then it would follow immediately, right? Let me write this part out. So there's the logic, right? That if you can show that this thing is a monotone class, then since it contains the collection C, which is really trivial to show, so I'm not going to bother, then it follows that the smallest monotone class, which is to say the one that we're interested in here, must be a subset of this particular monotone class. So that's the principle. That's what we're going to do, right? We're going to show that this M sub A is a monotone class. To show that that's a monotone class, we approach it directly. It is trivial to show that the universal set E is in M sub A, so I'm not going to bother with that. That's really, really obvious, right? If you just take E intersected with A, then you just get A. A is already in M sub A, so that's really easy. Okay, let's move on to the most, one of the interesting parts, which is suppose that we have some two elements of M sub A, right? And we're trying to show that M sub A is a monotone class. So what that means is we assume that we take two elements out of it and one is a subset of the other. We want to show that the relative complement must therefore be in M sub A. Okay, so that's the second property just applied in this particular setting. So that's what we're trying to show. Now, showing that this relative complement is in M sub A, by definition of what M sub A is, it's the same thing as trying to show that A intersect that set is an element of the monotone class. Now, let's note that by assuming that B and B prime are in M sub A, this is just telling us that A intersect each of them is in the monotone class. Now, some Venn diagrams may help us out here. So here is a picture of A and B prime and B. Remember, they may intersect, or they may not intersect, but this is just showing a Venn diagram where you try to represent it as generally as you possibly can. So I've got A and B prime possibly intersecting in some points and possibly not in others. But one thing that is important is that B is assumed to be a subset of B prime, so I have drawn it contained entirely inside of B prime, but also it may intersect A at some points and may not intersect at some points. Anyway, so this is an attempt at drawing a pretty convincing Venn diagram just to help us to think about this set A intersect B prime minus B and how we might show that it is a member of the monotone class. Now, we would like to try to represent this set, right? This is the set that is A intersect B prime minus B, and we want to try to represent that as some two sets that are each in the monotone class, of course, right, like that strongly suggests that we're going to be talking about these two things, such that they stand in a subset relation, right, because I'm going to try to leverage what I know about the monotone class, that it has those monotone class properties. Well, that seems to be, right, that A intersect B prime being this whole thing here, right, that's A intersect B prime, and it contains A intersect B, that's this part right here. Maybe I should color that something different so that we can visibly see when I'm talking about one thing versus the other. So they are in the subset relation, right? A intersect B and A intersect B prime, they are in the subset relation, and the Venn diagram hopefully convinces us, and you can give a set theoretic proof to make this rigorous, but hopefully we are already convinced that this set A intersect B prime minus B, which is the red portion that I've already shaded here, is in fact the same thing as what you would get if you took A intersect B prime and then subtract away A intersect B, right? So the Venn diagram hopefully convinces you of this equation, and so, right, like we've kind of got all the components necessary to infer, containment, right? So since we have the subset relation, then therefore, and because they are members of the monotone class, then their difference is also, their relative difference is in the monotone class, because the monotone class is closed under precisely those differences. So there we have it, right? We've demonstrated exactly the condition that is necessary to infer that B prime minus B is in M sub A. So this property is now proved. Okay, let's move on to the union property. So again, we're going to assume that we have a countable sequence of elements of M sub A. We're going to assume that they form an increasing chain. And by definition of assuming that they're in M sub A, we know that their intersection with A is in the monotone class. Now, we are clearly interested in taking their union. By the way, I guess I should also say, I should have remarked on this in the proof, that A intersect B sub n is itself a subset of A intersect B sub n plus 1. So it forms an increasing chain, right? So we have elements of the monotone class, they form an increasing chain. Therefore, by the monotone class property for unions, their union, which, by the way, actually, and what I should also say is that the union, by mere set theory, this equation is true, right? So that is justified merely by set theory, that the A can kind of move outside of the union. But we have that this is in the monotone class, right? Because the monotone class, by definition, is closed under precisely this kind of union, so we have an element of the monotone class. But because it is A intersect this thing, we are now able to infer that the union of the B sub n's is in M sub A. Okay, we have now confirmed all the properties which show that M sub A is a monotone class because because it is a monotone class which contains the collection C, then we now have that the monotone class is contained in M sub A. And by the way, like, what does that get us? Like, in some sense, like, let's kind of take stock of the upshot there. For this A, if you pick any element out of the monotone class, the intersection is in the monotone class. So effectively what this shows is exactly what we set out to prove, which is that if you take anything from the generator and anything from the monotone class, the intersection is in the monotone class. And we use this to prove the main claim. So We effectively reproduce the proof, but with a small tweak, right? So we are this time going to let A be anything from the monotone class, not just the generator. Again, we form the set M sub A defined in the same way. But this time, we want to show that M sub A is a monotone class and that it contains the generator. Well, the fact that this is a monotone class does basically deserve a proof, but it is exactly the same proof as what we just gave above. So since there's nothing really new there, I'm going to skip over that. But what about the latter part, that the generator is contained within this M sub A? Well, that's effectively exactly what the result, right? Not the method, right? Here I'm saying the method of proof is the same. Here I'm saying that this follows from the result of what we just proved, which is that if you take anything from the generator, then it has the property that if you take anything from the monotone class, the intersection is in the monotone class, right? But anyway, so basically this part here is guaranteed by what we just proved, and there you have it, right? Since this is a monotone class that contains the generator, this altogether entails that the monotone class generated by C is contained within M sub A. And so this effectively says that if you take A and intersect it with anything in the monotone class, you get something in the monotone class. But A was arbitrary, right? So this effectively says no matter which A you pick, you always get this result. So for any A in the monotone class, then for any B in the monotone class, you get that A intersect B is in the monotone class. Well, effectively, this just is closure under finite intersections. Of course, I'm only showing intersections for 2 sets at a time, but of course, you can just do a simple proof by induction to show that it holds for any n sets at a time. So there it is. I regard that as proof complete. As always, if any part of this was confusing, leave a comment. I might be able to address it in the comments, but if not, if it's a substantial topic or whatever, if you'd like me to fill in some part of this proof in some way, let me know, and I may make a clarifying video.